teen test, start thinking about whether you want to take a test double or if there's a test you'd want to retake. Because we'll figure out a day to start doing those. So if you're looking through your things and like, oh yeah, I remember this one, is definitely want to retake that. Just kind of start getting your stuff together. It'll be like a similar version of what you already had done. So if you're electing to do a retake, again, remember the score is capped at 85. So the max score you can get on a retake is 85. Otherwise, just take the double. It's free. You don't have to do anything for it. And we'll worry about kind of getting that stuff squared away next week. I'll probably make a Google form or something that I'll send out to you guys about what you want to do. Okay, doke. There's already a homework quiz drop and a homework assignment drop in from the seniors. I can't do that targeted to an individual, so I have to do it like blanket. So that's already happened or is currently happening. Every time something gets added in, that updates automatically to whatever the new low score is after you've added in. So the computer handles that all automatically. So just to let you know that there's not going to be a second drop from that, because that happened when the seniors had to do it for the seniors before they left. Not that there were any seniors in this particular section, but there were seniors in the other section, and I'm pretty sure I just did it for both sections. I'll double check that before the end of the year, and if it wasn't that, I'll let you know that, like, hey, I forgot, I guess I didn't do that for your section because there's no seniors in here. But I think that's what's going on. That being said, Chapter 15, no test. What could there still be for Chapter 15? Homework quiz. Okay, so you're not out on that one. But we will, looking at the dates here, I don't think there's any chance by Tuesday we're going to be ready to take the test on this stuff, Chapter 15. So we're just not going to try. We're just going to go at a normal pace and just be okay with that. I'm okay with it. It's less grading for me. One-arm grading is still a hassle. You wouldn't believe how hard life is one-armed. Yeah, like silly stuff that you wouldn't think would be, don't think about being really difficult is really difficult. Like opening any kind of a jar. Anything that has a twist, it's just like, help. So it's like a big ass. Anyways. All right. That being said, do you guys have questions from homeworks? We'll start there. Tessa? 16?
Yeah.
Sure. All right. So, I'm guessing I know what your problem is. All right. It says the population P in millions of people of New York State T years after 1800 can be modeled by the equation, yada, yada, yada. What is the population of New York in 1850? So what I'm really doing here is I'm plugging a value of T into this function. What value of T would I plug in? Would 50, because 1850 is 50 years after 1800. So the way I'm going to set this up is I'm going to put this into my calculator as Y1. And then I'm just going to use the Y1 of commands to do this, because it feels like I'm going to have to do a couple of different things here, and rather than typing this in over and over and over again, I'm just going to what the heck did I do here? I forgot the E. Ugh. Gosh dang it. You stupid thing. You know, I kind of like the, like where it does the math type, where it prints it out exactly like the way you like it, or the way it's written. But it makes it really hard to like, oh, I forgot something, to come back and edit stuff sometimes, and it just grinds my gears. All right, so I typed that into y1. I'm going to do vars y1 of 50. So I have 1.79. So remember that it says P is in millions of people. So really that's like 1.79 million people, right? Okay. It says, what will the population be in 2010? So what a value of T am I going to put in there? 210, because 2010 is 210 years after 1800. So that should be 19.16 million, right? So you could write that, or you could write like 1 million, comma 916,000, comma 00. You know, like you'd write it that way too if you want. And the last one, part C, is what is New York's maximum sustainable population? So hopefully you recognize that the function here was a logistic function. A logistic function has two asymptotes, one of them at y equals 0 and the other at y equals c, where c is the numerator. That will be your maximum sustainable population, that upper bound asymptote. So it's just going to be 19.875 million people. And that's all she wrote there, Tess. Does that work for you?
Yeah.
No problem, dude. Rita, I see your hand up.
Yeah, I just have like two general questions.
Sure.
So if it's like one of the questions were like asked like how many years after, and then let's say it was like 20.1 years after, would you round to like 2021 or say to 2020?
So I think if it says how many years after, you could just say like 20.1 years after 1800.
Oh, what if it says like what year? Like would I say like 2020 or 2021?
So I would just say between 2020 and 2021, I think would be fair. If it says what is the earliest year the population is at least this, then you'd round up. Or like what is the first year that the population would be greater than X, then you'd have to round up. Because in 2020, it wouldn't yet be at that population that you wanted. The next year that it would be in 2021.
Okay.
So like that's the verbiage where rounding becomes kind of sticky. Is that okay? You said you had a second thing?
Yeah, also for like the population model like ones.
Uh-huh.
And like it's like put T.
Okay.
If it says like every month, like can you represent that as T? Or does it have to be like T over like
So I would write that as like either T over 12,
okay.
where T is in months,
Oh, so you do.
or I could write as 12T, where T is in years. Either way of doing that would be okay.
So you just like clarify what T is.
Right. Yeah. So you'd state what T is, and depending on the question, maybe one or the other is the obvious. Like, oh, clearly they want, since they're asking how many months or whatever, I'd want to write it as T over 12 and use months. But if it's like how many years, and like using 12T would probably be, you know what I'm saying?
Yeah, that makes sense.
It's just less figuring out afterwards. But either is fine. Is that
Yeah, that makes sense.
okay?
Thank you.
Sure. Giselle,
Oh, maybe that's it.
13? Yeah, sure. So 13, you would have really needed to do like potentially 11 and 12 to really be able to do that. So for 11, I'm going to need to write my population model for Austin. So what I'm going to do is I'm going to pretend that 1990 is like year 0. So the T in my population model is going to be the years after 1990, which makes 465622 the initial population. And then to find the rate, I'm going to solve a system of equations. I'm going to have, well, I don't really, I guess, need to solve a system. I'm just going to then plug in 6565622 or 562 equals the initial 465622 times b to the 10th. So to solve for this then, I'm going to say that the I would take the 10th root, or divide by the 465 number, and then take the 10th root. So I'm just going to kind of type this all in so I don't have to write everything down, because it's kind of tough. But I'm kind of assuming, based on the question that you asked, you're able to do 11 and 12. So I'm not really doing anything like that you didn't know how to do here. I'm just kind of like talking through what I did. Stupid thing missed one of those ones I typed. There we go. Okay. So that's that. I have the two models. And what I'm going to do is I'm just going to graph them and see where they're equal. So looking at this, Columbus has more population than Austin initially. At 2000, Columbus still has more. I'm guessing by 2010, they'll have flipped because it's gotten pretty close here already. So I think that probably X max can be 30 years. I should see them switch within there. I don't know what the population is going to be, but I know it won't be less than the population of Austin. And I'll just round that down to 400,000, so it's a nice even number. And I know it's going to be at least 700,000 before they swap. So I'll just make like 1 million or something here. I'll overestimate it by a bit, just so I make sure I can see their intersection. But that looks like a decent window to me. Is that okay with what I did there, Giselle? Okay. Then I'll just hit graph. So here's my model for Austin. And in a moment, here comes the model for Columbus. And the point I'm interested in is this intersection where the two populations are the same. So I'll do second trace, intersect command. I've only plotted two things, so I can just press enter 3 times. And I get that about 13.5 years after 1990, so somewhere in between 2003 and 2004. Does that feel okay?
Yeah, I was trying to do it like
algebra. It's going to be really difficult.
Yeah, that was the issue.
Yeah.
Thank you.
Yeah. This one should scream like, just do me on the calculator.
Thank you.
Yeah. Yeah. You could do it algebraically, but you have to be really careful. And it's like, you got to like use some like, you have to use like the change of base formula for logarithms
Right.
when you do the log of both sides. And then it's just like, then you have to do some factor. It's a hassle. Within your capabilities, but like to say you're having problems with it is not unrealistic because it like is very tricky.
Thank you.
Who's next? Anybody else? Okie doke. All right, let's pick up where we left off last time. So we were talking about logarithms. And we had done expanding, so I think we'll probably need to do condensing. Let me find that spot in my notes. All right. So here we're going to be talking about condensing two logarithms. So the order that we apply our properties of logarithms for condensing is the opposite order that we'd apply our properties when expanding. So remember when we expanded, we did quotient, product, power. So condensing, we're going to do power, product, quotient. And since we're going backwards for a power property, instead of looking for an exponent inside the logarithm, we're going to be looking for a coefficient outside the logarithm that we can move into the logarithm as an exponent, right? We're going the reverse direction. We're trying to put many logarithms back together into a single logarithm as best we can. All right, so first things up is we're going to look for power properties here. Do we see any power properties? Yes, how many? Two. So the 3 and then the 2. Mr. Kulik, could I think about that as a negative 2? I mean, if you wanted to, you could. I'm not going to, but it would not be wrong to take that as a negative 2. If you did take it as a negative 2, what would the symbol out front of log base 5 of x to the negative 2 turn into? Plus sign, right? So that's okay to do it that way. I would not, but you could, and you'll still get the same answer. It'd be okay. All right, next up, we're going to look for a product property. What is going to indicate a product property? Addition between the two logs. So we see that we have that there. And the last thing we're going to look for then is a quotient property. What are we going to be looking for a quotient property? Subtraction. So we see subtraction here. However, no quotient property applies in this situation. Why not? The logs have different bases, yeah. So because the logs have different bases, you can't actually apply any property of logarithm other than the power property on those. So you can't combine those together into a single log because they're different kinds of logs. One is log base 5, the other is log base 4. So this is as far as you could go on this one. It's a trick one because you really want to make one logarithm here, and it's really easy to ignore the subscripts there and just kind of go bulldozing away. But that is not a typo on that problem. That is just there to illustrate that, hey, the base of the logarithm matters. Okay. So let's look at the next example. What do we start looking for? Power properties. Do you see any power properties? Yes. How many? 3. So, because we have 3 coefficients, that'll make 3 power properties. We have to be a little bit careful here, though, on that middle power property. When I move that 3 inside the logarithm, how would I write that? Prater, what'd you say? Okay. So the exponent of 3 would need to apply to both of them, or you could write it with an exponent or a parenthesis around both of the 2, or you could write a cubed, b cubed. Either would be okay. Eventually, I'm going to end up at a cubed, b cubed. I'm going to write it this way to start with, but it would not be wrong to skip this intermediate step if you saw where it was going already. So far, so good? All right. Next up, we look for product property. Do we see any product properties going on? Yes. Why do you say that? Because of the addition. Oops, I guess we used blue before. Let's keep those the same. What 2 logarithms should be we combining together with the product property? Not the 2 last terms. Should be those 2. Why not the middle one? Why does the middle one not get involved in a product property? Not because it already has AB in it. Because it's negative. The product property is going to combine 2 positive logarithms together. I know that I can add things in any order I want. So commutatively, I can put those 2 logarithms that are positive next to each other with the plus sign in between them. Doesn't change the value of the expression, right? So when I'm applying the product property, it has to be positive logs going together. I can't take a positive one and a negative one and combine them together with a product property. Is everybody okay with that reasoning? Okay. And again, picked a problem where it was designed to trick you, right? So that I can talk about these finer details. All right. Last thing we look for is quotient property. Do we see one? Yeah, because of the subtraction symbol. And they're the same kind of logarithm this time, so they can certainly go together. Does it matter which one is the numerator and which one is the denominator? Yes, good. Which one should be the numerator? The positive log, right? Which one should be the denominator? The negative log. Well, I shouldn't say the negative log. The stuff inside the negative log, right? So there's that. Everybody's happy. What do you notice that we can still do here? Yeah, you can reduce this, right? So just down to natural log of A over B. I'm going to do one more bonus one because there's one other thing that happens quite frequently that throws students for a loop. So I'm just going to take it in a very simple example just to illustrate what this is. First thing we look for is power properties. Do you see any? No. Okay. Next thing you look for is product properties. Do you see any of those? You should. There's one hiding. Anybody see where it's hiding? Braden? Yeah, between y and z. Very good. Let's factor off a -1. And then we should be able to see that hiding product property there. Oh, Mr. Kulik, this is so sneaky. Right? We see it now, right? So if you have more than one negative logarithm, there is some product property kind of hiding in amongst those negatives, right? So when we did that factoring, and now we can see that product property there. And then the quotient property to just finish us out. That is maybe the most common mistake I'll see students make when trying to handle these, is doing something like that, missing the hidden product property. It's okay? All right. Let's talk about now solving. So we're going to start with exponential equations. We'll do a couple of examples of those, and then we'll move on to logarithmics. So let's say we have 14 times 1/3 to the x minus 1 is equal to 126. So any way that we want to solve this, we'd want to start first by getting the exponential part by itself, which would mean we'd want to divide both sides by 14. (126) divided by 14 is 9. Everybody's happy with what I did so far? Now there's really kind of two approaches we could take here. The first approach is I could try to rewrite 9 and 1/3 so that they have the same exponent base. What do you think that would be? What base could we write both 1/3 and 9 with? 3. Okay? So 1/3 is 3 to the negative 1. And 9 is 3 squared. When I have an exponent of an exponent, those multiply. And now, since the bases are the same and the two things are equal, the exponents must be equal. So if I subtract 1 and then divide by -1, I get that x is -1. The other approach that I could have would be to try to cancel the exponent base of 1/3 using a logarithm. Which logarithm would I choose to use here to make this as easy as possible? Log base 1/3. I'd want the base of the logarithm to match the base of the exponential. Any log will work, but like it's a heck of a lot messier. And I'm not about that life. My life is messy enough, trying to do everything one-armed. So those cancel each other out. So then we'll add 1 to both sides. And then it's calculator time. So remember, to get the log base command, you're going to press the math button, scroll all the way down to the bottom to where it says log base. You can type in the 1/3, 9, and then outside the parenthesis, the +1, and you get the same -1 value. Does it matter to Mr. Kulik which way you do this? Not a bit. Which way does Mr. Kulik think is the better method? I like the second way. The reason I picked the second way is it doesn't matter what the numbers involved are. So if, say, this was the number 8 instead, would have been a very difficult problem figuring out a way to rewrite not 8 and 1/3 to have the same exponent base. It's possible to do this, but it's not trivial. In fact, you would end up having to use a logarithm, which is the exact same. So it's really the same process. It's one is we're just hiding the use of using a logarithm when it's convenient to like not have to write it down. But in general, I would just assume just kind of be doing it this way every single time, because I don't have to worry about what happens if it doesn't work, right? Now let's try a similar example. So you guys tell me, what would you like, what should we do first? Okay. Divide both sides by 12. So I'm going to reduce that as I go, right? 27 and 12 both have a factor of 3. You should recognize here that it would not be difficult to write these with the same exponent base at this point, right? 9/4 is just 3/2 squared. So if you wanted to do that, you are more than capable or more than welcome to do it that way. And in a problem like this is probably what I'd end up doing. It's just not typically my first option. But if it's sitting there staring at me like, please don't use your calculator to do this, I'll take you up on that offer of not having to use my calculator. Everybody's happy there? If I wanted to do this with a logarithm, which logarithm would I want to use to both sides to make this as easy as possible? Log base 3/2. Again, the goal there is to make the log base and the exponent base match. So those just cancel each other out. And then log base 3/2 of 9/4 is just 2. Again, I just did that a second ago, just without a calculator. And then multiply both sides by 5, and I get x equals 10. Everybody's okay here? Let's look at the most difficult kind of exponential problem we'll ask you to do. Would be something that looks like this. What do you notice that's different about this one than any of the previous examples? Has division in it, sure, but that's not that big of a deal because it's just being multiplied by 1/4. We have, the variables in two different places, right? Yeah, that's the troublesome part. What do you suppose the first thing we'd want to do is? Yeah, let's get rid of the fraction, so multiply both sides by 4. Now my next order of business is to try to get rid of the negative in the exponent. How would I do that? I have that negative exponent, right? I have 3 to the negative 1, or negative x. I want to get rid of that negative exponent. So I have all positive exponents. What can I do to do that? What? I'm sorry. Oh, make it a fraction, sure. Yeah, so we could write that as this, right? Okay. Everybody's happy with what we did there? No more negative exponent. What do we pick up instead, though? That we're not a fan of. A fraction. Okay, well that's fine. My next order of business then is to get rid of the fraction. What can I do to get rid of the fraction? Great. Yeah, let's multiply both sides by 3 to the x. When I multiply 3 to the x by 3 to the x, what do I get? Definitely not 9x squared. So you could write it as 9 to the x. You could write it as 3 to the 2x. Or you could write it the way that I would write it. And I'm just going to write it that way. 3 to the x squared. Everybody's okay with that? Okay. 3 to the x times 1 over 3 to the x is just going to be 1. And then 8 times 3 to the x, I can't do anything to, right? Because the exponents are different and the bases are different, so there's no combining that can happen with that multiplication. Not 24 to the x. I know it's tempting to want to write that. Is everybody okay here? What does this kind of look like to you? I have something squared, something to the first, and a constant. What does that look like? Quadratic, yeah. So let's move everything onto one side, because I know that to solve a quadratic, that's what I'm going to have to do. And then I'm going to transform this from something that looks like a quadratic into something that is explicitly quadratic. So I'm going to just replace those 3 to the x's with a different variable, y. Everybody's okay with what I've done so far? Okay. Now we know how to solve a quadratic, right? How can I solve this? Okay. 2 things that multiply to give me 1 and add to give me -8. Can't factor it. Okay, so what do we do if I can't factor it? Quadratic formula, right? So y equals negative of -8 plus or minus -8 squared minus 4 times a times c over 2a. So negative of a negative is positive. Negative 8 squared is 64. Minus 4 is 60. If I simplify that, I think that's 2 root 15 over 2. And then I can reduce that just to be 4 plus or minus root 15. But we're not done. What variable are we supposed to be solving for? X. What variable have we solved for? Y. So what do we need to do? We just need to put that 3 to the x back in for y. Is everybody good so far? Okay. How do I solve each of these two equations? What do I need to do to solve those? You need to use a logarithm. Great. The logarithm I should use is log base 3. Yes. Again, exponent base 3 cancels log base 3s. And now it's just calculator time, right? So math. Scroll to the bottom, grab my log base command, type in my 3. I'll do 4 plus square root 15. And then I can just go and update that to be minus. So I have 188 and negative 188. What do you guys think? Are we okay with this? That's probably the hardest exponential one that you'll get to deal with. Which again, the trick is just making it into a quadratic, using our quadratic methods to solve the quadratic part, then turning it back into an exponential and solving the last little piece, right? This is like the moral of the story for all of Algebra 2 is that every function eventually solving problem turns into a quadratic equation at some point, right? You see that over and over and over again. So let's do some logarithmic equations now. So here we have 3 times log of x squared equals 6. First thing I'd want to do is get the logarithm by itself, so we'll divide both sides by 3. Okay. Now, what I would do is I would think about canceling that logarithm. What's going to cancel the logarithm? Exponent base 10. So I'll do like, and I'm going to write really exaggeratedly big 10s. So when I'm going back and looking at this, I'm not confused and thinking that that's multiplying by 10, because I'm not multiplying here, correct? Okay. Really important. So x squared is equal to 10 squared. So what can we say x is? No. Plus or minus 10, because you took the square root of both sides. But logarithmic equations, the domain for a logarithm is not all real numbers. So it's a possibility now that we've acquired an extraneous solution through the act of solving a polynomial. So every logarithmic equation needs to be checked. The check is easy, though. All we're doing is checking to make sure that if we plug in for x, we don't get a non-positive inside of our logarithm. So if it's 0 or negative, bad news bears. If I put 10 in for x, I get 100. That's no problem. If I put negative 10 in for x, I get positive 100. Still no problem. Both of these answers are acceptable. I would keep both of them. Everybody happy there? Okay. Let's look at maybe the most complicated logarithmic equation that we'd ask you to solve. Would be something like this. What do you notice that's different about this one than the previous one? Yeah, we have multiple variables and multiple different logs. Great. What's my first order of business going to be? I need to condense this into a single logarithm. So I'm going to move everything onto one side, and then it's going to become just like the problems that we did at the start of the lesson. Oops. So I'll do my power property first. I'll do my power property second. I'm sorry, product property second. And then do my quotient property last. So far, so good. Now I need to get rid of that logarithm. What is going to get rid of that ln? Exponent base e. Again, I'm going to write really exaggeratedly comically big e's here, so that if I'm going back and looking at this, I don't accidentally think that I'm multiplying here. And e to the 0, again, is 1. Remember, any non-zero number to the 0 power is 1. We're now have to solve this. What kind of an equation are we left with to solve? It's a rational equation, right? So my first order of business is I'd want to get this turned into a polynomial. So I'm just going to multiply both sides by x squared. And I'm going to FOIL that thing as well as I go. that right? Nope. That middle thing wasn't right. It should be minus 3x and minus 2x is minus 5x. Okay. There we go. So far, so good? This is quadratic now, so I'll get everything onto one side, so I'll subtract x squared from both sides. And now to solve this quadratic, we could either try factoring or the quadratic formula. Since the leading coefficient is 2 and not 1, I'm not even going to try to factor. I'm just going to use the quadratic formula. This would factor. If you wanted to go through that route, you're welcome to do that. But it's like just as long as the quadratic formula is, in my opinion. So I'm just going to use the quadratic formula because I'm guaranteed an answer there. And I feel perfectly confident using it. If it was a leading coefficient of 1, I'd certainly try factoring it. But I'm just not interested in the hassle for this one. So negative of a negative is positive. Negative 5 squared is 25. 4 times 2 times 2 is 16. 25 minus 16 is 9. The square root of 9 is 3. So 5 plus 3 is 8, divided by 2 is, or 4 is 2. And then 5 minus 3 is 2, divided by 4 is 1/2. But we're not done. What do we still need to do? Yeah, so I'm going to go all the way back to the very beginning. If I plug 2 in, oops, not even there even. I need to go all the way back to the original problem. If I plug positive 2 in, I get all positives inside the logarithms, right? So that one's good. So I'll circle that. If I plug 1/2 in, though, what do I notice? I get a negative number in the first logarithm already. Do I care what happens in any of the subsequent logarithms? I do not. If I get one non-positive along the way, that's bye-bye, Billy. So that one would be extraneous. Or is there always going to be an extraneous solution when we solve a logarithmic equation? No. What if it's a quadratic that I'm solving? No. Still could get you 2 workers, or it could give you no working solutions even. That's possible as well. So you really do need to check every time. And you're not guaranteed to get any. Or you could get all of them. You just don't know until you check it. There's still a little bit more to this solving chapter, but it's all like application, and I feel like I just want to wait and save that to next time, especially if we're not in a rush to get a test crammed down your throats here. But at the end of the semester, I have a feeling there's going to be enough other teachers trying to do that Mr. Kulik can just take a pass on it. You're welcome. We would say, though, that you can now do homeworks 83 through 130, which probably makes it even as good a reason as any not to go any further, because that's a bunch of numbers all right there. Some of them are just used like the change of base formula. You know, like, I don't know, 5 or 10 of them are just like, do the change of base formula on this. Like, that's not, it's where you write like log base 2 of 3 in your calculator is like log of 3 divided by log of 2. You just put it in your calculator. It's like a 10-second problem, which is like, oh, okay, well, those ones are at least piece of cakers. Anyways, that feels like a good stopping point for today. Next time we'll finish 15.4 and probably start and or finish 15.5, depending on how motivated we're feeling. So yeah. And again, what can we still expect? Homework quiz.
like next class.
Might be a good time for one. Okay. Everybody happy so far? At least as happy as you can be. Got 20 minutes left. Get a start on that. That's a lot of numbers I just gave you. Get some of those, crank some of those out. What's up,
I feel
Prudence?
like the homework quiz would be like everything up to 82. Or would it be like this stuff?
Yeah, that's a good question. Probably through 82.
Okay. Thank you.
You're welcome.